All right, now we're going to look at rigid body impulse momentum. So the first thing we're going to do is figure out the angular impulse of a rigid body. And we'll do this the same way. We'll look at a single particle within a rigid body. Okay, it has a velocity. It has some distance away from some arbitrary point P. Okay, and by definition, my angular momentum is r cross mv of that particle. Okay, so just moving m to r and then vi, the velocity of I, relate that back to the velocity of p using our relative motion equation Vp plus omega cross r. Okay, plugging what I know about that. So for r, I'm using basically x and y. Okay, so that's where this guy comes from and this guy comes from. Omega is in the k direction, and then Vp has an x and y component. Doing all of these cross products, I get that the HP of point I is excuse me, given here. So my VPX, mx, VPY, and m omega r squared. And we've done this a few times now. Taking this cross product, that's what you get out. The r squared comes from, eventually I'm going to get x squared plus y squared times omega. Gives me that. So I just do that r. Again, we've done this a few times, so just kind of cut to the chase there. Okay. Now, doing this for the entire rigid body, basically I sum up all of the angular momentum for each of the particles, and that's effectively doing an integral. Okay, so changing all the mi's to dm's essentially is what I'm doing here, and I get an equation that looks like this. Now, as we've done several times before, if I set p equal to the center of gravity, then the first two terms go away because they are in effect the center of gravity, the equation for the center of gravity. If I set g equal to p, then that center of gravity is at 0, so those all go away. And all I'm left with is omega times the integral r squared dm, which is, of course, the mass moment of inertia I. So the angular momentum of a rigid body is I omega. Okay. Now, doing this for rotation about a fixed axis. Okay. Basically, I have a rotation as well as a translation. So I have I omega plus r cross mv, which is what I have there. Okay, and this is for rg, which is the distance from the point to the center of gravity that I'm looking at. Okay, then knowing that the velocity of point g is equivalent to r omega, okay, if I've got this pure rotation, okay, I can separate this out, and of course I have my parallel axis theorem. We've done this a few times at this point. So I can simply write the angular momentum about point O as I-O omega. Okay, should be no surprises. It's very similar to things we've done with energy and whatnot. So now getting to my equation, my angular impulse momentum, I'll start with Newton's law for rotation. Sum of the moments equals I alpha, where alpha is d omega dt. Okay, bringing dt over to the left side. Okay, I'm left with this equation right here. Well, the integral of d omega is just omega 1 minus omega 2. And I'm left with this bottom equation down here, which is the initial angular momentum plus the angular impulses equals the final momentum. Now remember, momentum is a vector product. So I have linear momentum, x and y, and then my angular momentum shown here about the center of gravity. Okay, so I can apply all three of these equations as opposed to when I had simply the energy equation where I only had one equation. So again, these are the equations you apply. They relate velocity and a force to time, okay, or angular velocity to a moment to time. Okay, so that's the equation you use. Just remember it's a vector equation, so you have up to 3 equations that you can use for a planar problem.